Hey, welcome back to your favorite calculus class. Good to be with you guys again today. We're going to talk about applied optimization in this section, so some application problems to these derivatives. We're going to talk about solving these first. So here's kind of, you can look through these 5 steps. I actually kind of like to summarize it with the acronym GUESS. Oops, let me see if I can get my draw to go here. So when you're doing these applied optimization problems, it's always good to guess. This is just kind of a general way to approach any story problems, which is to evaluate who your givens are in the problem, identify what your unknowns are, what are you looking for in the problem, identify any equations involved, whether they're given explicitly in the problem or just implied implicitly. Like you should know, you're dealing with a circle, so area of the circle is pi r squared or whatever. And then you're likely to probably have to substitute, make some sort of substitution, typically with a given or maybe some unknown that you had to solve for. Make a substitution and then you'll solve. And that's solve using if you're doing just algebra stuff, algebra. If you're doing, like these applied optimization problems, you're going to be doing some sort of calculus involved with it. So again, I like to guess when I do my story problem. So let's talk about what's the smallest perimeter possible for a rectangle whose area is 16 square inches. So we know, uh, with a rectangle, if we got length and width, and all we're given here, what are our givens? Well, we're given the area. Number one, our area, which is length times width, that's given to us. That's 16 square inches. 16 is length times width. And then it's asking us what's the smallest perimeter possible. So one of the um, implied equations here would be your perimeter. So you got length plus width plus width. So 2L plus 2W, right, is your perimeter for this rectangle. And this perimeter is what we're trying to minimize, right? We're trying to find the smallest. Well, to minimize something, to find a minimum, we know we can take the derivative. So I'm going to use this perimeter equation. But the problem with this perimeter equation is right now it's in terms of both length and width, right? P equals 2L plus 2W. So what I'm going to do is I'm going to go ahead and solve for the length over here. And I'm going to substitute that in over here. So then I'll have my perimeter just in terms of width. So my perimeter is 32 over W, or 32W to the negative 1, plus 2W. And this is what I'm trying to minimize. So I'm going to take the derivative of the perimeter with respect to the width and set it equal to 0 to find the value of that width that maximizes our perimeter. All right, so number 3, let's take the derivative with respect to width. So we got 1 dp dw equals, and over here we're just taking the derivative with respect to w. So we got negative 32 w to the negative 2 plus 2. Now we're going to set this equal to 0. So 0 equals negative 32 over w squared plus 2. So we've got 32 over w squared equals 2. 2w squared equals 32. W squared equals 16. So our width is either plus or minus 4. Well, we know negative width is not an option, so we know our width um, has to be 4 that would minimize this perimeter, right? Because we took the derivative of the perimeter and we're minimizing it, right? I mean, if we're doing the first derivative test, what this is saying is we have a minimum at 4, right? It's going to increases then decreases. I'm sorry, decreases and then it increases. So we have a minimum at 4. So now we need to know the dimensions of this, right? The length length times width dimensions. So since the W is 4, our only option to minimize this thing, and we know our length is 16 over W, so our length is 16 over 4, which is 4. So length times width, 4 by 4, is the dimensions, right? So the smallest perimeter, so number 6, smallest perimeter, 2 times the length, 2 times the width. So we got 16. It's our smallest perimeter. Okay, just a blank shape to work there. All right, here's another applied optimization problem. We got a rectangle, has at its base the x-axis, its upper two vertices on this parabola y equals 12 minus x squared. What's the largest area the rectangle can have, and what are its dimensions? Okay, so you know what? Let me draw a picture of this thing. We've got y equals 12 minus x squared. Let me write that, negative x squared plus 12. So we're up here at 12. So we got a quadratic flipped around. It's bumped up 12 here, and it's hitting something like this here. And then a rectangle has as its base on the x-axis. So on the x-axis, we have the base, and then the upper vertices are on the parabola. Okay, so somewhere on the, let's put it right here, here. Okay, so we've got this rectangle. All right, here's our rectangle. Okay. Again, this parabola is y equals 12 minus x squared, or negative x squared plus 12. So, what is the largest area? So we're trying to maximize our area of the rectangle and then find the dimensions. So what's the largest area? So first of all, we want to say, well, number one, what's the area of this rectangle? Well, this point right here is the point x comma y right here, and it's a distance out x and a height, I don't know what it is, but it's up y, right? So it's a distance x. So this whole base would be x plus x, so 2x, right? So that's like our length is 2x of this, and then our height here would be y, because it's hitting right there on that parabola. So length times your width, or length times the height there, so 2x times y. And now what we're going to do here is I'm saying, well, I got to take the derivative because I'm trying to find the largest area, right? I'm trying to maximize area here. But the problem is I have x and I have y. So let's make a substitution. We know that area, or the y is 12 minus x squared for the parabola, right? So let's go ahead and let's substitute that in. So we've got area is 2x times 12 minus x squared. So we've got our area is 24x minus 2x cubed. Okay. Now we're trying to maximize this, right? So I have area and it's only in terms of x right now, which is great because now I can take the derivative with respect to x, so I can try and maximize it. So derivative of the area, derivative. So we got 1 dA dx equals 24 minus 6x squared. I'm going to set this equals 0. So we've got 6x squared equals 24, x squared equals 4, x equals plus or minus 2. X is a length, so I know x equals 2 will maximize that area. An x value of 2 is what we want, right? We want this distance, so it's at 2, it looks like. We want to go out 2, right? X equals 2 will maximize the area. In other words, this first derivative test we're maximizing it, so it's going to be increasing, and that's going to the function, of course, is um, up until 2 for the area. That's describing the area function, 2x y, or 24x minus 2x cubed. So x equals 2 is going to maximize this. So then the question becomes, what's the largest area? Well, if x equals 2 is going to maximize it, let's plug it in to our area function that's only in terms of x. So area, plug 2 in, we got 24 times 2 minus 2 times 2 cubed. We got 48 minus, what's that, 16? We got 32 is the maximum area. Now, the last part of this does say, what are the dimensions, right? So the dimensions are, it's 2x by y, right? 2x by y. Dimensions are 2x by y. So 2 times, we know the x is 2, and then it's by our height, which is the 12 minus x squared. Well, our x is 2. So we got 4 by 12 minus 2 squared, 12 minus 4, 8. So this is a 4 by 8, are the dimensions. 4, that's 8. 4 by 8. Okay. Move on here. There's just some room to do those. All right, you've been asked to design a 1 liter, which is 1,000 cubic centimeters, can shaped like a rice cylinder. What dimensions we use? The least material. So what dimensions we use? The least material. So well, first of all, let's start with what we're given here. We've got this volume. All right, we got a liter here, which is 1,000 cubic centimeters. So I want to think to myself, well, number one, the volume is the area of the base, pi r squared. You got your r here, times the height, h, pi r squared h. And they tell us it's 1,000 cubic centimeters. All right, so r is in centimeters because r squared would be square centimeters. Height is in centimeters. It should be height, right? That's why it's a cubic centimeter. And then what we're trying to do, number two, is we're trying to use the least amount of material. So uh, how much material do you have? So geometrically speaking, what we're talking about is your surface area. Surface area. Now, the surface area, if you look that up for a cylinder, would be 2 pi r squared, because you got your pi r squared on the bottom, you got a pi r squared on the top. So there's 2 of those pi r squareds. And you've also got this part. Imagine if I cut this and unraveled it, the length of this thing would be the circumference, and then it's times the height, right? If I cut it and then unraveled it out like a rectangle, if you will, that's the surface area of that portion, not including the top and bottom. So that would be the circumference, of course, is 2 pi r, so it's 2 pi r, but then it's times the height. So that's the surface area for a cylinder. That's what we're trying to minimize. So we're going to take the derivative of that surface area. Now, right now, I don't want to take the derivative because I got 2 pi r squared plus 2 pi r h. I got r and h involved. So let's make a substitution for h right there in terms of r. Now we know that 1,000 equals pi r squared h. So if I divide by pi r squared, 1,000 divided by pi r squared is going to go in there for h. So this becomes surface area. 2 pi r squared plus 2 pi r times this h that's going in, 1,000 divided by pi r squared. So we got 2 pi r squared plus 2,000 divided by r, right? That cancels, that cancels, that cancels. This is one of those r's right there. 2 times 1,000, 2,000. So here's our surface area in terms of r, right? And of course I could, that's the same as 2,000 r to the negative 1. So let's go ahead and take the derivative here. You know what? I'm going to go with a clean sheet here. What was our surface area? Our surface area was 2 pi r squared plus 2,000 divided by r. So we're taking the derivative. Step, what are we on? Step 3. Oh, come on. Surface area derivative with respect to r. So we got 4 pi r, that's a pi right there, and then minus 2,000 r to the negative 2. Okay, we're going to set that equal to 0. So I got 0 equals 4 pi r minus 2,000 over r squared. 2,000 over r squared equals 4 pi r. I'm trying to find my r critical points here. So 2,000 equals 4 pi r cubed. R cubed divided by 4 pi is 2,000 divided by 4 pi. R cubed is, what's that, 500 over pi. Now I'm taking the third root. So the third root of 500 over pi, that's what our radius needs to be to use the least amount of material, right? So we want, for this cylinder, we want a radius to be that. So if you punch that in, 500 over pi to the 1/3, and 5.42 centimeters. Okay. So now, back to the question. Let's see if we answered it. What dimensions we use the least in material? Well, we just know the radius right now. We really need to know the height as well for this thing. So let's go back here. Now we know that the height, if you remember from back here, the height is 1,000 over pi r squared. So step 4, now that we know the radius, 5.42, but I don't want to have rounding error on that, so I'm going to use 500 over pi here. That's 500 over pi. Height was, what was that? That was 1,000 over pi r squared. So we've got the third root, or 500 over pi to the 1/3 squared. So in other words, to the 2/3. So you punch that in. Ends up being 10.84 centimeters. All right, so there's your radius, 5.42. There's your height if you were to round that, 10.84. Or there it is in exact form above there. Okay. All right, so let's go to vertical motion now. The height above ground of an object moving vertically is given by, so you got this position function, right? Got some sort of um, position function where, I don't know what this thing looks like. S is your height in feet, t is in seconds. Find the object's velocities. Well, find the velocity. We got to take the derivative of the position. So, whoops, v of t, which is s prime of t. So we take the derivative, negative 32t plus 96. And so what would the velocity be when time is 0? So velocity at time 0, oops, that's a plus 96, and that's gone. 96, of course, position's feet, and velocity would be feet per second, right? Position, feet, velocity would be feet per second, right? Changing position over changing time there. And then your acceleration, feet per second squared. They don't ask about acceleration here, but just to remind you on those. So here's your velocity, 96. This is feet per second. All right. So that's at 0 seconds. What's the maximum height? So the maximum height's referring back to the position, right? So we want the max height. So the maximum position. So we already have the velocity function, v of t equals negative 32 plus t plus 96. So this, if I find my critical points, this will help me to understand who will maximize my position, right? The velocity, which is the derivative of the position, will maximize, will show me the potential points for a maximum. So let's add 32t to both sides. So 32t equals 96. Divide by 32, so t equals 3. So your max height, right, this s prime, which is the same as velocity, this, which is describing this position function. So it's saying that that's your only option. It increases and then it decreases, of course, right? Being a parabola, right? It's going to increase until 3, and then it decreases after. So you've got a maximum there at 3. So what's its maximum height? Well, let's plug it in. We know it occurs when t is 3. So s of 3, so we got negative 16 times 3 squared plus 96 times 3 plus 112. Let's put that in here. 56, what that'll end up being. That's in feet. So that's your max, right? So it occurs at 3 seconds, the max height is 256 feet high. All right, part C. What's its velocity when the position is 0? Well, I don't even know what time. I need to know what time this thing hits the ground, right? When is the position 0? When does it hit? At what time does it hit, right? So when does the position 0? When is the height 0? When is the position 0? Let's find the t first, and then once I have that time, then I can plug it in and find the actual velocity for when it hits the ground. So let me take a 16 out. Let's see, that'd be t squared minus, factor that. These are parentheses right there. So I got t equaling 7. I got t equaling negative 1. Well, we know I can't have a back in time. I can't be negative 1 second. So it's at 7 seconds. That's when that object hits the ground, right? At 7 seconds, that's when the position is 0. So what would the velocity be? Well, let's plug it into the velocity function. The velocity is negative 32 times t, which is 7 in seconds, plus 96. So negative 32 times 7, 24, plus 96, negative 128 feet per second. So that's the velocity. It's going 128 feet per second. That's the speed. And of course, it's going in the negative direction because it's going down, right? It's impacting at that velocity, 128 feet per second. Well, thanks for listening. We will see you next time.